All right, students, I've been grading these and getting a little closer to getting done, but I thought maybe this would be a good time to take a little break and make you a video solution here and watch through this, learn from your mistakes. You can even self-grade here, get an idea of where you did right and what you did wrong. Let me just dive right in here. So you took exam number 2 on Tuesday, and so it says, look at the circuit in the figure, find the currents, the voltage, and the power in each of these resistors. All right, so there's a lot of ways to handle this, but the first thing to recognize is that even though like this 30 and the 40 are in series, which we could combine to a 70, or this 50 and 20 are in series, we could combine also. It doesn't really matter if we do that now or later. We will see that ultimately you cannot make a reduced circuit out of this. So we're going to have to do the Kirchhoff's loop rule and the node rule. And now it's just a matter of defining which currents you want to call which one. It kind of looks like, to me, the current is going to be dominated by this stronger battery. So in this middle loop, I'll say the current goes up. It gets to this node, and now they're fighting here, pushing in. But it looks like my guess would be this one wins, and it goes that way. And hard to know on this one. And then that's really my point, is we don't try to take too much time here and figure out which way the currents go. Just let's just make a mark here. All right. And just for lack of better numbers, I'll call that current 1, this one current 2, and this one current 3. And notice as it wraps around, current 2 goes through the 20 and also goes through the 50. So there's no point in labeling another current down here. That's just going to make it look like a harder problem. So current number 1 goes through the 9-volt battery, then the 30 ohm resistor, and then the 40 ohm resistor. Okay. And now we just need to make a series of equations, and it looks like we will need 3. And maybe you guys remember me saying I think the best thing to do is to do the small loops, and however many small loops you have, which in my case is 2, would then tell you need 1 node, because we need a total of 3 equations. So whatever you do, don't do all 3 loops here, because they're not independent equations. So I guess I'll do this equation over here on the right first, and it looks like plus 20. If I imagine myself starting at the bottom of this battery and moving forward, I go increase in potential. Here I go with the current. So it's minus 10I3. As I hang a right here, I go to the lower end of the battery. So that's minus 3. Here I go with the current. So it's minus 20I2. Again, going with the current, minus 50I2. And then I get back where I started. And in fact, you can kind of see how you would be combining these mathematically in a second. This would be minus 70I2, and that's the same thing you would have written if you had said, let's combine those two at the beginning. And so this would be equation number 1, although let me clean it up a little bit. Maybe I'll put the 20 and the 3 together, so that makes a 17 equals. And then I'll take this one to the other side and also this one to the other side. So this would be a plus 70I2 and plus 10I3. And I'll leave a little space because there's no I1. And so I'll call this equation number 1. Now, let's do the other loop, okay? And maybe I'll start here again, and this time go up the center loop and then go left and back where I started. So this is 20 and then minus 10I3 against the battery, that is from the big one to the little marker. That's a minus 9 volts. With the current would be minus 30 I1, and then with the current again is minus 40 I1, and I get back where I started. So the total sum of the voltage changes equals 0. That's the conservation of energy. And again, like we said in the first equation, you can see how these would be now combined together, whether you do it now mathematically or earlier in terms of simplifying the circuit. And then kind of working this out, you'll see if I put the 20 with the 9, I get an 11. And if I move this to the other side, it becomes a plus 70 I1. There is no I2, leave a little space, and then 10 I3, and so I'll call that equation number 2. And then finally, now that I've done the 2 loops, knowing that I have 3 unknowns, so I need 3 equations, I need to come to a node, and we'll see that either node would give us the same thing because you've got 1 and 2, in this case going out, or in this case going in. So the sum of all the currents going in equal all the currents going out. And so looking at this bottom node, these 2 are coming in, this one's going out. Or looking at this top node, this is coming in and that's going out. Which of course can be written as I1 plus I2 minus I3 equals 0. And so there's equation number 3. Which then we can write in matrix form and use our calculator to solve it. All right, so taking this first equation, looks like it equals 17, and there is 0 I1, 70 I2, and 10 I3, okay? Looking at this second equation, looks like it equals 11, and there is 70 I1, no I2, and 10 I3. And this last equation equals 0, and there's a 1, a 1, and a negative 1. All right, so letting the calculator do the arithmetic here, I will get what I1, I2, and I3 are equal to. All right, so let's go to my matrix and let's do an edit, and we will need a 3 by 4. And inputting it here then would be 0, enter, 70, enter, 10, enter, and then 17. On the next row will be 70, 0, 10, 11, 1, 1, negative 1, and 0. And let me just check. 17, 11, 0, good. Next column over. 10, 10, negative 1. 70, 0, negative 1. And the first column, 0, 70, and a 1. Okay, perfect. So I guess I'll quit that. I've got that matrix in there. Okay, now to actually let the calculator do the work, let's do a math operation. Scroll down until we get to the reduced row echelon form, and then we can select matrix A. So this is saying, you know, take matrix A and do a bunch of operations called a reduced row echelon form, which would turn it into that. So there's the unity matrix, and it looks like I get a current of 0.113 for number 1, 128 for number 2, and 0.311 for current number 3. And of course, to fill in my little chart now means I need to give some careful consideration to what was meant by this one, current number 1. Current number 1 is the one that went through the 9-volt battery, and then also the 30 and the 40, so these two. So this is 0.113, 0.113. Okay. Number 2 was the one that went through the 20 and the 50. So 0.198, 0.198. And the big one here, which is the sum of the two, is the one that goes through the 10 ohm resistor, and that's 0.311. All right, so that's the main amount of work. We've got some more here to do. To get the voltage, we could just use Ohm's law. We've got, anytime we got 2 of these, we can find the third. So just multiply these 2 together, and I'll get the voltage. So this would be 311, since I'm just multiplying by 10. 0.198 times 20 would give me a 3.96. 0.113 times 30 is 3.39. 0.113 times 40 would be 4.52. And finally, the last one would be 9.9 volts. And then finally, for the power, we could just go current times voltage, or we could go I squared R, or we could go V squared over R. Kind of the choices are. I'll just do the IV here. So 0.311 times 3.11, and that is a little under 1 watt. Okay. 3.96 times 0.198, and that's 0.784. And then 3.39 times 0.113 is 0.383. 4.52 times 0.113 is 0.511. 1.198 times 9.9. It's the most power, almost 2 watts here. And so 196. So there's my different powers for this circuit, and of course my different voltages, and then the corresponding current. So check that one off. That was a good one, and maybe a little bit on the long side, but certainly not an unexpected one. We did a lot of those in chapter 28. And also in 28, we did something like this, where we had a resistor in series with a capacitor and a power supply and a switch. And this one says, calculate the current coming out of the battery 25 milliseconds after closing of the switch. Now, you might want to remember that we got this equation, that it was the initial current with this exponential decay to it, where the initial current, I'll put this over here, was the current you would get right when you close the switch. And if you remember, when capacitors then are uncharged, you can think of them as just a wire, because if you were to add the voltages around the loop, you would say that there is no change in the voltage there. So you would just have a 9 volts here and then minus an IR. So it would look something like this. 9 minus the IR returns to 0, so I just is the 9 divided by the resistance. So this would be 9 divided by 6, and I'll write it as a K. It would be a little easier to calculate, because 9 divided by 6 is 1.5, and a K means 1,000, so this would mean 1,000, so that'd be a milli, and the units would be amps. And so this then becomes 1.5 milliamps for the initial current, E to the minus, and then I'll put the 25 milliseconds. And then this part is the time constant for an RC circuit. So this is the resistance times the capacitance. And one thing that might be a little tricky here is what do I do about the fact that I've got two capacitors instead of one? Well, I'd say we're going to get the equivalent capacitance. But they're right, they're not next to each other. Are they in series? Are they in parallel? Well, maybe the best answer I can give you is back to the calculation we just did, where you'll see when you add them up in a loop, if they're in the same branch of the circuit, they're going to show up as two terms that can be combined like they're in series, like they were next to each other. But notice that if this term had been over here, you still could combine them because mathematically they're equivalent. And that's what I'm trying to say here is if you added up around a loop here, you would have something, that looked maybe, I'll put it up here like this. You would say, okay, there'd be a 9-volt battery. Then there would be this minus the voltage on capacitor 1. Then there would be this IR. Then there would be minus the voltage of capacitor 2. Then you would say 0 when you completed the loop. But see how these are just mathematically the same as if they're right next to each other. In other words, they're still in series. Whether they're adjacent to each other or there's some element in between, doesn't matter. They're still mathematically in series. Series means they have the same current. So if there's anything challenging on this problem, it might be this one here, where you go, oh, yeah, these are in series. And so that might take a moment to kind of digest that. But they are in series. So I will do capacitor 1 and take its reciprocal, and capacitor 2 and take its reciprocal, and then take the reciprocal of that to get the equivalent. So grabbing my calculator, the first one is a 10 microfarad, so I'll take its reciprocal. The second one is a 5 microfarad. So there's the two added together, and I'll hit the equal button, the reciprocals, and then to take the reciprocal of that answer gives me my 3.33 microfarads. And then taking that and multiplying it by my 6 kilo, and so maybe I'll go 6, 1, 2, 3, and multiplying it by my 3.3333 times 10 to the negative 6 for the micro. We're looking at, and there's some rounding here, but you can see because it's a perfect fraction, that should be 0.020. So I'm going to just put 20 milliseconds, or 0.020 seconds. So this would be 20 times 10 to the minus 3. So this becomes 1.5 milliamps times e to the, and the milli will cancel, and I will get 25 over 20, which reduces to 5 over 4. And so let me take my e to the negative, and depending how you want to write this, I'll just go 5 over 4. Maybe I'll just hit enter. So that's about 28% of the original 1.5, and we are looking at 0.429 milliamps after 25 microseconds. Yay! All right, so that's 2A, and that's kind of our standard charging up a capacitor. This one, number 2, is kind of the other extreme. This asks for the current in the battery the moment the switch is closed and after a long period of time. And so the logic being is, like I said back in A, when you first close the switch, you can think of this as a short circuit. So I guess I would kind of write it this way. That when I first close the switch, this capacitor is a short circuit. And I'll pause right here on my drawing, but I hope you kind of see now this is in parallel, really. This would kind of be the equivalent of having this resistor and this resistor coming down and meeting up. So these two are in parallel, but it gets even better than that because this one here is branching down. And actually matching, since we're going to treat that capacitor as a straight wire, they're matching down at the bottom. So this circuit here, when it's first closed, is really saying that we have three resistors in parallel. And so to get the equivalent resistance, like we did up here for capacitance, we would have the reciprocal of the first one plus the reciprocal of the second one plus the reciprocal of the third one, and then reciprocate all of that. And maybe to make it a little bit easier, why don't I just call that 3 times the reciprocal of one of them, and then take the reciprocal of that. Okay, so what is the, all resistors are 25. So if I take 25 and take its reciprocal and multiply it by 3, and then take the reciprocal of that, this is the equivalent of about 8.33 ohms. So the current in this battery would be 5 divided by 8.3333, and 5 divided by that last number is 0.600 amps. So that's the current coming out of this battery, and then dividing, and we can, well, we're not asked to, but we could figure out how much current goes through each of them. They'd be equal, so it'd be 0.2. It's a nice even current divider because they're even resistance. But we can stop the first part the moment the switch is closed. So that's the first part of this is 0.6. Now, the other part of this is after a long period of time. And after a long period of time, the capacitors become full and they don't let any current flow through them anymore. And so our phrase was, after a long period of time, we can treat capacitors as an open circuit. And so in this case, the current would go through the first one, the second one, and then the third one, and then complete. So these would all be in series now. And so the equivalent resistance would be resistor 1 plus resistor 2 plus resistor 3, or just 3 times one of them, which makes the 75, since one of them is 25. And so the current then would be 5 over 75, which I guess is 1/15, which is a fifth of a third. Oh, how about I write it as a 2/3 over 10? Yeah, because 2/3 is 0.66. So that would be 0 and then 0.666 repeating 2/3. All right, so there is the current after a long period of time. So you first close it, you get a lot of current, capacitors charge up, stop the current down different branches, and eventually decays down to this much. And I'm glad they didn't ask us how it decays down. That would be a fun problem. I think that's really not for this class. That's getting more into our circuits class. So you guys in circuits probably did all this Thevenin resistance and the decay constant and the general solution of a decaying RC time constant. But for us, we'll just do the two extremes. All right, well, hope that helps. Maybe I'll look at my time now taking the test. Remember, I give you 25 minutes per problem, so it looks like I'm just shy of 25 minutes. So I'm on a good pace here. I'm not going to run out of time here. Okay, so let's go on to problem number 3. Where is number 3? Aha. and try to solve this one here. Now, problem number 3 says we're going to find the magnetic field in this crazy thing. Now, let me just remind you, we had the magnetic field from a straight wire worked out for us. And so why don't we start there, because we've got 2 straight wires. And let me go ahead and write the equation for the straight wire. We also had a ring along the axis of symmetry. Didn't give myself much room to write here. And this is the general equation. But in our case, we're going to then have a half of a ring, and we'll be in the plane of the ring, so the x will be 0. Well, more on that in a second. Why don't we just find the magnetic field from this straight wire right here? I'll call it from A to B. And so let me take my yellow piece of paper here from A to B. And if I draw in here, that perpendicular distance is A. So let me fill this out. This would be mu naught times I over 4 pi. And I need to take a moment to figure out what A is. Now it says here the long wire, let's see, the current flows straight for 1 meter. So this distance is 1 meter. And so that means if I think of this cut in half, this half is a half a meter. And it would be cut so that this would make 2 45 degree right triangles in here. And so this distance also must be 1/2. So there's my distance A away. And then the swing angle would be 45 degrees, that is, drawing from the perpendicular distance to the start of the current is 45 degrees. And the other swing distance, or swing angle, is a 45. But using our grid as positive and negative, our angles, that would be a negative 45, which, of course, sine being an odd function means you can change that to be a positive if you bring that out in front. So this becomes mu naught times I over 4 pi, and then we have the 1/2, and then we have a 2, because there's 2 of these, and then we have the sine of 45, which is root 2 over 2, which those would cancel off. And I suppose we could take one more nice step. Mu naught is 4 pi times 10 to the negative 7. Okay. And that will allow the 4 pi's to cancel off. And so bringing this 2 to the top makes an 8. Root 2 and times 10 to the negative 7. So that's the magnitude of it. Now, doing the direction, I need to do my right hand, and so I'll pretend like I'm grabbing the wire with my thumb in the direction of the current and watch my fingers as they curl around, so it would be going in to my paper here, or into your screen. Okay, so that's the first one. Because then when I do the second straight wire, I can see exactly the same setup, so it's going to be the same magnitude. So if I call this B to C, I will say the magnetic field from B to C at least has the same as A to B. And if I look at the directions, and I say magnitude, but when I look at directions, it looks like, oh, it goes in to the paper also, or into your screen. All right, so they're together. And so the two of them together, and so BC and AB would be double that. So 16 root 2 times 10 to the negative 7. Which, if I change that into a decimal, 16 times the square root of 2 gives me about a 22.6 times 10 to the negative 7, maybe better written as 2.26 microtesla. And so I'll change that to 10 to the minus 6 and call it a micro. Okay, so there's the amount from the two straight pieces. So now let's do the arc. I'll call it B from C to A. And maybe I'll do the direction first. And so the current is flowing along this ring, taking my right hand, what we called right hand rule number 2, and now using my fingers for the current, my thumb giving me the direction of the field is into the paper or into the screen. So it's going to be in the same direction. So whatever magnitude I get, I just need to add it here. There's nothing canceling off. So that's kind of nice, nothing canceling off. Just got to add them together. They're all in the same direction, which ultimately will mean it's into the screen. Okay. Calculate the magnetic field. Direction, yeah, and magnitude. So I got the direction. So the direction is into the screen. And so now I will write this equation here. And notice that if we're at the center or in the plane of a ring, which is what that x meant, that would be 0. So if that goes away, then this r squared with the square root makes the r cubed. And oh, that was a poor writing on my part. I apologize. Sometimes we write this as an A, and sometimes we write it as an R. But these are the same, and so you would end up with just an A cubed, and 2 of those A cubes would cancel off, and you would be left with just an A downstairs. So this is our equation for a full ring when we're at the center of the ring, and we only want half of that. So we've got mu naught times the I over 4A, and the A being the radius. So we got a little bit of thinking to do in terms of the A. It would be this distance here, which again, recognizing that this is 1 meter and this is 45 degrees, A would be 1 meter times the sine of 45 degrees, which is root 2 over 2. And so I'm going to put that into this equation. So this becomes 4 pi times 10 to the negative 7 times 4 for the current, and then 4, and then this would be a root 2 over 2. And of course, kind of depends how you want to attack this one. Maybe I will, well, do the easier step and just cancel off the 4s. Maybe I'll imagine this 2 flipping up to the top so that this root 2 into 2 makes that a root 2 and goes away. And so it looks like in terms of magnitude, I have a 4 and then a root 2 and then a pi times 10 to the negative 7. So grabbing a calculator here, I've got 4 times the square root of 2 times, whoops, that is not a pi, times a pi. And it gives me a 17.8. 17.8 times 10 to the negative 7, or 1.78 micro Tesla. Okay, now the final step is to add these two together. So I got 2.26 from here and 1.78 from here, resulting in a 4.04 for the total, and then units are the micro Tesla. So 4.04 micro Tesla is the answer to 3A. Nice. Now 3B is a lot like 3A. We're going to have to use our multiple loop turn, and we're going to have to use this equation really twice here. I guess it would look something like this. The problem says we've got these two loops. I'll call them Helmholtz coils, since he famously designed these coils. There's a nice property about them. We use them in the E/m experiment, but when the separation of the two coils R is the same as their radius, you get a nice uniform field in the center. However, we're not using them here in this problem as a Helmholtz coil. We're asked, or we are told, that the field is 0 over here, and that's because the currents are in opposite direction. They said the current flows counterclockwise in the left loop and clockwise in the right loop. So somebody standing over here counterclockwise, the left loop is going to make a field going this way, B left, and this one over here, the right loop being clockwise, would make a field going this direction, and so I'll call it the magnetic field from the right loop. But we're told at this point that the field is 0. And so mathematically, we don't have to, mathematically we have to say that the right loop equals the magnitude of the left. We don't need to say what direction they are. So that's kind of nice. We don't, need to get bogged down into that part of the problem, but it's kind of nice to see that they are opposite in direction, that they will cancel off. You can even see that the right one being further away then is probably going to need, not just probably, definitely going to need a larger current. And so all the other things are the same, like the number of turns, the radius, it's just further away. So this must have a bigger current. Now, they say the left one has a loop of 5 amps. So keeping that in mind, I know that this needs to be greater than 5 in order to have the same strength further away, in order to cancel those off and get 0. I guess that would mean right here as a Helmholtz coil, we would have something pointing in the left direction here, and we've got a battle between these two, which doesn't seem like a good design if you're trying to get a uniform field here. You'd want the currents in the same direction. You don't want them battling each other. But this one is, again, the fields are battling each other. All right, so with that in mind, I will do a calculation just on their magnitude. And so the general equation for a loop is, let me just repeat what we wrote here. And I'll put current, but I'll put current right loop. For the radius, this time I will use the symbol R, since that's what they have for the radius in this symbol. And then it's a 2, and then it's an x squared plus an r squared to the 3/2. And that needs to equal then the mu naught times the current in the left times its radius, which is the same, and its distance away, which is not the same, but radius is. And I suppose I should put also a factor of n in here, because there are many turns to it. And so this is the field I'd get from the right one, and this is the field I'd get from the left one. Now, fortunately, this actually comes out to be an easy calculation, because the problem says the left and right loop have the same number of turns. So that cancels off. A mu naught shows up on each side. A 2 shows up on each side. A radius squared shows up on each side. And then this reduces to the current in the right loop over x squared plus r squared to the 3/2 equals the current in the left loop over x squared plus r squared to the 3/2. Now let me move this one over to here, and if you're not careful, you might think they cancel. But this is actually the x from the right loop. So maybe I should put a little r down here. And this is the x from the left loop. So I'll put a little L there. And so this gives me the main equation to solve this. What is the current in the right loop? Well, it's the current in the left loop. So there's the 5 amps. And then now I can put in my different values of x and r. And it wouldn't even matter which units I use because they'll cancel off. So I can put x and r in the centimeters given, or I could switch them to meters, or I could switch them to inches for that matter. But I have a tendency to kind of focus on meters, so I'll do that. And so the distance from the right loop, you might have to think about it because it says it's 0. Where is it here? The magnetic field on the axis of symmetry, 15 centimeters from the left. So this distance is 15, but yet there's another 20 here. See, the r is a 20. So that's 35. So this is 0.35 squared. And this is 0.2 squared. Whereas the distance from the left loop is only 15, and then of course the left loop also has a radius of 20. So again, this would be 5 times whatever this ratio is. And so let's see if I can get that number, 0.35 squared plus 0.2 squared. And so that's the numerator. And in fact, save myself a little calculator work. Why don't I just factor out raising it to a power of 3/2? So that's the numerator. Let's go with the denominator, 0.15 squared plus 0.2 squared. And that's the denominator. So taking the numerator and dividing it by the denominator, there's my ratio, 2.6. And if I raise it to 3/2 power, I get about 4.2 times the original 5 amps, meaning we would need roughly 21 amps in order for this to cancel off. So you can see that it's further away and it needs more current. And not just a little more current, over 4 times more current. You can see that it's, you know, almost double the distance here. A little less than double the distance from this one. But we have to increase the current by quite a bit because of this multiplication factor. All right. Nice. All right, let's move on to number 4 then. And so number 4 is asking, what is the resistance of this crazy thing? Now, there's a couple different ways we can do it, but I'll just set it up the way I did it for the homework problem and see how that works for you. The first thing to recognize is we learned that the resistance of some little piece that is some length L and some cross-sectional area A with some resistivity rho has this much resistance. And so if you had something that kept changing its area, which is what happens here, the current enters and we have a area first, which would be pi A squared, and then it gets bigger to pi B squared, and somewhere in the middle, it's some area in between. this number keeps changing, and so we're probably better off to think about a little resistance would equal to a little bit of length over whatever the cross-sectional area is at that moment. In fact, maybe I'll even just write the cross-sectional area as pi r squared, where r, again, is the radius wherever you are. And so the radius is going to start small at A and eventually get bigger at B. And so to get the total resistance, I have to add up all the dRs. This would be in series. This would be, if you could imagine cutting this into discs. And each disc gets a bigger cross-sectional area. That's really what I'm doing here. And so each little disc has an area that gets bigger. And the length, I might as well just call it the x-axis instead of the dl. Make me feel a little more comfortable with my calculus. I'm used to thinking about this horizontal as being an x-axis. And so that's what we're going to do. We're basically going to integrate from the beginning here, which we'll call it x0, and keep adding up until we get the end of this, which would be x equal to L. So there's I'll call it the first half of the problem, really setting up the integration to figure out what the resistance is going to be. And now we've got another little tricky problem here. And so let me put my grid system on here and kind of draw this top edge, which would represent a line, but it would start at a height of A and then finish at a height of B when you've gone a distance of L. And see, this line right here would represent what the radius is if you are thinking of this as cutting slices. So a cross-sectional view might look something like this. And so again, the first cut, the radius would be A. Then they would get bigger and bigger and bigger and bigger, and so the radius would get bigger, and the last one would have a radius of B. And so the radius would be the equation for this line. Y equals mx plus b is kind of our uniform equation for a line. And so if I think about this y really being the r, I can just say, okay, this is r. This is the radius. This is what I'm hunting for in this equation because this radius changes. And then the slope would be the rise over the run. So it looks like the rise is how much bigger is B compared to A. So there's the rise. And the run is this distance L. So we get the rise over the run. And then B is the intercept. Don't confuse it with that B. B, and the general equation, is an A in our case. And so this gives me the mathematical equation that I need for this integral. And so this would be a B minus an A over an L times an X plus an A. And then squared. So that, again, would be the radius. And the limits would be my 0 to L. Now, at this point, it's probably good to do a U substitute so that I would have something that looks like this. U squared in the bottom. And then here, I need to take the differential So if I take, set this equal to u and take the differential, I get a du on one side. And on the other side, I get a b minus a times a dx, or b minus a over L, that number, and then the dx, and the differential of the a is a 0. So that means if you imagine moving the L to this side and then the b over to a to this side, we get the value of dx. And so we can say that the dx is equal to L over b minus a times the du. And if we pull out factors that are constants, like the rho and the pi, and now the L over the b minus a, we have an integral that's pretty easy. It's just a 1 over u squared, which I will write by putting the u squared up at the top, and so I get u to the negative 2. So that when I do the integration, I get u to the negative 1 over negative 1, evaluated from beginning to end. And so, maybe I'll put in the beginning to end here. We could switch this back to an x. In this case, and I usually do that, but in this case it might be better to leave it as a u, because if you come back to the limits, the starting one, if you think of the u here, when you put in a 0, that just makes an a. So the beginning part of the u is an a. And the ending part is also kind of nice, because if you put in x equaling to L, those cancel off. And then you have a b minus an a, and then when you add the a, you're just left with a b. And so the limits are a to b, which is a nice limit. Usually you get crazy limits after you do your u sub, so I always like to go back to the x before I put in my limits. But in this case, I noticed it was going to be a nice one. So let me leave it that way. So I'll put the negative in front of the rho and the L. And then, of course, this is 1 over u. So this would be 1 over b minus 1 over a. Which, if I simplify, I can get a common denominator of b times a. So this would be a minus b. And if I put that negative in here, this then becomes a b minus an a. So I'll get rid of that negative and cancel that off. And that's nice because b minus a is what I have on the bottom. B minus a cancels with b minus a. And so I get a rho times an L, and then a pi, and then a b times an a. Ah, nice. And so now it's just a matter of putting in my numbers. And so let's see, what did they say the numbers were? 731, and I should put in the unit ohm meter here, because the length they give in centimeters, and I need to watch that, so I'm going to change the length and put it as a meter, so now I get a meter squared, which is perfect because that meters squared in the top will cancel with the meters squared down here if I put them in meters, and I'll just get an answer in ohms. And so let's see, the B is in millimeters, so 0.0023 when I put it as a meter. And the A is given in millimeters, so I'm going to put it in as meters. And so now the meters cancel off, and I'm left with units of ohms. So then when I do my calculation, I get 731 times 0.0194. Then divide by a pi, and also divide by 0.0023, and divide by 0.002, coming up with 4.0 981, and that'll be thousands, so why don't I just put kilo ohms? So 981 kilo ohms. So quite a bit of resistance for a short thing. So the resistivity is really poor. Be fun to look that up. It's probably the equivalent of, I don't know, hate to guess on that. Seems high, but it can be a lot higher than that. So it's not that high, but it's not a good conductor by any means. It's probably like a brick or something. Okay. So there's my number 4. And then finally, number 5. Where's number 5? Aha. Number 5 says that we have a proton that's accelerated. So in other words, there is some charging plate that's got a little hole in it like we did in a lot of our experiments. In this case, we'd make this plate negative, and we would release the proton here, and hopefully some of them would make it through the little hole. Most of them, as we designed in our lab, would hit the negative plate, but many of them would make it through the little hole and be going very, very fast. And so these were accelerated by some voltage V sub A. And if you remember doing this in the lab, we used the 35 volts the first half of the lab, and then the 70 volts. So there's our accelerating voltage. And it says here the proton is accelerated by an unknown voltage, and it heads towards a magnetic field from the left as drawn in the colored path. And so it kind of comes up and curves around. Okay, the proton enters a region where the magnetic field, so this is this area, and so that's why it begins to bend now. In fact, I'll just write that we know that there is a magnetic force on a moving charged particle in a magnetic field. So moving charged particle in a magnetic field would have this much magnetic force on it. And so this is our chapter 27. No, 29, sorry. The last one I just did was 27. The magnetic field is perpendicular to the motion. Okay, so the motion is here. So that means the magnetic field is either coming in or out of the screen if it's perpendicular. The proton's path is a half circle, and then it exits the magnetic field. So it does this half circle. Makes sense. As soon as it enters the field, there's a force, and a force is always perpendicular. That was our Physics 121 that would give us a circle. In this case, it's a half circle because now it exits, and so no more magnetic field, so now it goes in a straight line. And so here's the first part of this question. Is the magnetic field going into the screen or out of the screen? In other words, in this region, should I be drawing little X's or should I be drawing little dots? And you can kind of see it here. We know then that the force, like right when it enters, must be towards the center of the circle. So the force is right there. And then there's the V going from left to right, and then we've got the B. And so I guess if I were to try to get my right hand over here to do this, I guess I'd have something that looks like, I'm going to have to turn a little bit, like this. I put my fingers in the direction of V, close towards B, so my thumb can go up. So B must be going down into the paper here, or into your screen. So I guess there's the first part of this. What is the direction? The direction is into the screen. Okay. And now, of course, they give us a little information. They say the distance between the incoming path and the outgoing path is 1 centimeter. That's important because 1 centimeter cut in half, so a half a centimeter, would be then the radius. All right. So if we use a combination of our chapter 29 together with Physics 121, we would say this QVB, and then we get the sine of 90 degrees since the field is going into the screen and the proton is moving in the plane of the screen. And then that has to equal to mv squared over r. canceling off a V and rearranging this, we would have QB over here. We can even put an R over here, an M down here, and get a V. And so that's kind of the first half of the mathematics, is saying, okay, use the information given, I can get the velocity. In fact, maybe I will. So velocity equals, and so the R is the 0.005. Q is the charge of the proton, 1.602 times 10 to the minus 19. B, that's the size of this magnetic field. So a pretty strong magnetic field going into the screen, 1.5. Very strong field, I guess I should say. And then the mass, 1.67 times 10 to the negative 27 is the mass. And so if I put all those together, 0.005 times 1.602 times 10 to the negative 19 times 1.5 divided by 1.67 times 10 to the negative 27, I get a speed of 7.19 times 10 to the 5 meters per second. So moving very, very quickly, obviously, as it arcs around. We're, like I said, partway done. We still got a little bit more to do here because this is the speed. Now my question would be, all right, what is the accelerating voltage? Well, this is where we get work done is equal to change in kinetic energy. Change in kinetic energy would 1/2 mv squared. The work would be the charge times the accelerating voltage. And so the accelerating voltage would be this kinetic energy, 1/2 mv squared, divided by the charge that of the proton as it accelerated. So maybe I'll write this as a 2 in the downstairs part and then put the charge, 1.602 times 10 to the negative 19. I'll take the mass again, 1.67 times 10 to the negative 27. And then the velocity I just got at 7.19 times 10 to the 5 and square it. All right, since I already got that in my calculator, let me just hit the square button and multiply it by 1.67 times 10 to the negative 27. Let me divide that by a 2 and also divide it by 1.602 times 10 to the negative 19. And we're looking at about 2,000, I'll just round it to 700. So 2,700 volts is what would need to be applied to this plate, or it doesn't really matter, it could be a cylinder like ours, so it's not a uniform field. As long as it has this much voltage, it gives this much work, which gives it this much speed, which would make it turn by this radius when it's in the magnetic field. All right, ta-da, all done. And, oh good, only took us an hour 3, so now we got some time to double check things before we submit them in. All right, hope that helps anyone. Bye now.